So hello everyone. Good afternoon for most of you. My name is I'm Dr. Amilton. I'm speaking from the University of Sao Paulo in Brazil. So I'll talk about a little bit about my research topic. It's a recovery of critical metals from electronic waste in Brazil. So I'm working in the laboratory of recycling waste treatment and extraction, the LAREX, here at the Polytechnic School of the University of Sao Paulo, Department of Chemical Engineering. So here we are 4 professors, almost 40 graduate students from master's and PhD students, 7 postdocs, a lot of undergraduate students, and a few technicians. So here am I in the photo. We have a huge laboratory for experiments in aqueous media, also in thermal treatment, equipment for chemical and thermal analysis, chromatography, X-ray diffraction, TOC for carbon organic and inorganic quantification, KMS, and so on. So here it's me. I'm chemical engineering, master in chemical engineering and PhD in chemical engineering for a few months. I have more than 50 articles published. And then here is my email address. So if you would like to send me an email, a question, or invitation for everything, just send me an email. So we're going to start why e-waste recycling. What's the importance of recycling e-waste, electronic waste? So that's the image from the Wall-E movie from Disney. That's the main topic of this movie is how much garbage or waste have in our Earth in a future, not so long future. So that's the main topic of the movie. So let's start a talk. Let's talk about it. What's the problem of how much the garbage, or in this case, e-waste we generate every day? What's the problem, and what we can do to solve this problem? So there is a museum in UK that in front of the museum that there is this sculpture called WEEE Man or e-waste man. So it represents how much e-waste we generate in our life. So this structure has more than 3 tons and 7 meters tall. It's a huge structure representing the problem of e-waste generation in our life. E-waste is everything of electronic equipment that changes technology or it's broken, or we cannot use anymore because new technologies are coming. So I remember when I was young, this type of computer, I think you can see my screen. You can we had huge computers in our desk. Now we have just small notebooks or smartphones working as well as a notebook, and our technology has evolved from a huge smartphone, or actually cell phones in the beginning of the 90s. And now we have smartphones better than computers used in Apollo 11, for instance, when the first man went to the moon. Our technology in our pockets are better than that. And also TVs has changed a lot. So those TVs are now e-waste, we call as electronic waste or e-waste. When we see this electronic waste, when we take a look on that, we can see those those wastes are composed of at least 60 or 70% of all periodic table, as we can see here. So we have a few elements that are presenting batteries, or touchscreen, or cases, or circuit boards. So at least 60 or 70% of electronic periodic table of the elements are presenting our smartphones or cell phones in our pocket. And most of them are considered critical or strategic elements or metals for in several countries around the world because of the problem with supply chain, interruption of supply chain in the next years. I mean, the next years, in the next 5, 10 years. So this problem is related to interruption of supply of these elements for everyone in the world. For also, a few elements such as the earth elements are concentrated, are mainly concentrated in their production in China, for instance. So China represents almost 90% of the whole production of rare earth elements in the world. It's the same as cobalt. Cobalt production in the world is concentrated mainly in Congo, in the central of Africa. So these elements here highlighted their production are concentrated in a few countries. That's why those elements are considered critical or strategic elements in the USA, for instance, Europe, Brazil as well, Japan, China, and so on, because of the because of the interruption in the supply chain, the medium and in the short and medium term. When we observe the recycling rate of these elements around the world, we can observe that most of them, or at least 90% of those elements, their recycling rate is lower than 50%. Here we are I'm representing for you a few elements such as cobalt, iron. The recycling rate of iron is really pretty much high in the most countries. Here in Brazil, the recycling rate of aluminum cans is almost 95%, 96%. But when we observe the rare elements, the recycling rate is lower than 1%. And those elements are really important to produce electronic equipment. And the increased demand for these elements to supply this market put a lot of pressure in the extraction from primary sources, from the nature. So it's really important to think about the recycling of electronic waste to supply the market, with these elements. And when we compare the content or the concentration of these elements in primary sources in the ores from the nature with the e-waste, the electronic waste, or from or equipment from or smartphones or notebooks, we can observe that most of them, there are more in our smartphones, the content in our smartphones is higher than in the nature. So for example, cobalt, the concentration of cobalt in our smartphones can be almost 20 or 50 times higher in your smartphones than in the nature. So that shows the importance of recycling to obtain these elements and supply the market. When we observe it, for example, gold, silver, and palladium, we can achieve more than 1,000 times of these elements more concentrated in your smartphones than from the nature. And this problem is highlighted when we observe the amount of e-waste generated per year. The amount of e-waste generated have been increasing every day, every year. That's because more people want to buy these smartphones, more people can buy such smartphones or electronic equipment, and then a few years later, those equipments are becoming a waste, a kind of waste. Here in Latin America, when we compare the e-waste generation, we can observe a correlation between the GDP and the e-waste generation. For example, here in Brazil, we have the highest GDP in the Latin America and also the highest e-waste generation. But when we compare with Mexico, we have 50% higher GDP, but almost double, twice e-waste generation. And when we compare the generation per capita between the top 3 countries, Brazil, Mexico, and Argentina, we can observe that there's a situation here to be think about it. Here in those countries, we have a lot of social inequality, and most of those equipments are bought. A few people buy such equipment than others, and as more and more people are buying these equipment, there are more people that can buy such equipment, the generation will be even more higher. But the main problem here is the amount of e-waste formally collected. The data for Brazil is the poorest in the Latin America, in the top 5 economic countries here. We have almost 0.14 kilotons of e-waste formally collected per year, while in Mexico is 36, Argentina 11, and Colombia 3, and Chile and Peru 6 and 3, respectively. Probably the main reason for that is the national legislation, policy, or regulation. Brazil has a national legislation about waste in general. Here, we have this legislation, this national policy that include e-waste, while Mexico and Argentina, they have a specific e-waste policy, national policy. So one of the reasons that the e-waste collection is too small, is too poor, probably one of these reasons is that our national policy is not specific for e-waste. So probably in the next years, we should change it, create a specific e-waste policy. Also, Brazil is responsible for 40% of e-waste generated in Latin America. When we observe the size of Brazil, we have a huge problem. Brazil is bigger than almost all the whole Europe, for instance. Brazil is the biggest country in Latin and in South America. So the problem here is how can we recycle or create an industry to recycle waste in north of Brazil or in the southeast, and how those e-waste will travel from the north to the southeast to be recycled. So here we cannot create only one company or only one industry to recycle the whole e-waste here in Brazil or in South America. We have to create a lot of points, recycling points. So for this, the only technology we have to design a small company, a small industry to recycle e-waste from a small region, for example, in the southeast or in the south of Brazil, is using hydrometallurgy route. The hydrometallurgical route is a process that the reaction occurs in aqueous media, so in water, with water. So how it works? So the raw material, in this case, the e-waste, after the physical procedure, the physical process, is reacted with a leaching agent. A leaching agent is a water mixture that may be acid or alkali. So that can be works in acid media or in alkali media to dissolve all those elements to the aqueous media to be mixed with water. Then, after the leaching step, a purification and separation steps are required to obtain different products. For example, a copper concentrate solution, or cobalt, or nickel, aluminum, gold, vanadium, earth elements, to obtain a rich solution of these elements separated, and then to obtain the product, the metal, for example, copper metallic, or a compound, which can be cobalt sulfate, or nickel oxide, nickel carbonate, and so on. That depends. So hydrometallurgical route, the main advantage is to make possible to obtain small companies spread around the country. So that's the main reason. And I have here a few examples of my research group and how to recycle these e-waste by hydrometallurgical route. First of all, batteries, they are really important to our notebook or smartphones or any equipment using IoT. But the main battery here that I will focus is to supply electric vehicles market. So I will focus on it in my presentation. So the main reason is that there is an increasing demand to supply, to sell such batteries, to change our cars from using oil to use cars using electricity as power energy. These batteries are different. They can be different. We have cylindrical cells, prismatic, and pouch type cells. All those batteries are composed of a metal or plastic case to protect the battery. Separator made by plastic, PP or PE. Anode made by graphite, and the cathode is the richest part of the battery that may be composed of different types of oxides, metallic oxides, and also phosphate of lithium iron. That there are different technologies to make the battery. And such batteries, each one is a cell, is called as a cell, and a group of cells is called a module, and a group of modules is a pack that we have in the car. So we have a pack of batteries in the car, and then a module and a cell. I have here an example of a process. It's a patent to recycle NMC batteries. They are lithium-ion batteries composed of nickel, manganese, and cobalt in the cathode. So the first step after the physical procedure is the leaching using sulfuric acid. So it's acid leaching. After filtration, carbon is obtained, so it can be separated. And then a precipitation to remove iron and aluminum. Solvent extraction is a liquid separation using organic phase to obtain cobalt, nickel, and manganese. And finally, lithium is obtained by precipitation as phosphate or carbonate. And then it's possible to obtain cobalt, nickel, and manganese sulfate separated or together. About printed circuit boards, the main reason that it in this presentation is that most of our smartphones, or almost not, all smartphones and computers and notebooks have a PCB, printed circuit boards. So that's the reason it's really important to study and create a plant to recycle these e-waste. These PCBs, they are different according to their use. For example, memory board is mainly composed of ceramic and have 18% of metallic fraction. Motherboard, 36%. Printer board, 44% of metallic fraction. 63% of smartphone board in smartphone boards, and in PC video board, 36%. And the main reason we have to pay attention in metallic fraction is that the main compound is copper. Copper is the main element in PCBs and in metallic fraction. Their content is pretty much higher than in the primary source. We have at least 1% of copper in the ores found in the nature. In your smartphone, we can find at least 10 or 20% of copper in the whole PCB. So I have an example here how to recycle PCBs. So after the physical procedure, the non-magnetic fraction goes through the leaching procedure that can occur in two steps. First, we're using sulfuric acid to remove nickel, aluminum, zinc, and iron. And secondly, the second step is using sulfuric acid and hydrogen peroxide to obtain copper and silver. Or you can do a single step using sulfuric and hydrogen peroxide to obtain all those elements. Most of the literature use nitric acid concentrated to obtain copper from PCB, but we found that it's possible to use dilute solution of sulfuric acid, 1 mole per liter, less than 5% of sulfuric acid, and with the hydrogen peroxide together to leach copper from the metallic fraction to the aqueous media. So that's possible to use sulfuric acid diluted to extract copper. And then after the leaching, copper separation can be occurred by solvent extraction that using a few organic extractants such as TEPA, is a type of organic extractant, by several steps, first to remove zinc and aluminum, and then to obtain copper. And after the re-extraction, after the stripping procedure, to remove copper from the organic phase to the aqueous phase, it's possible to obtain a copper-rich solution with low concentration of impurities. So that's important to prepare copper sulfate or metallic copper. Okay. Another possibility is to obtain silver from PCB and also synthesize silver nanoparticles. So after the leaching, the leach solution, in the leach solution, silver is recovered using sodium chloride, and then it's obtained a copper solution concentrated here. And then silver is solubilized using ammonia hydroxide, and then silver nanoparticles are synthesized by Turkish method. Finally, the photovoltaic panels. It's important because the increased demand and the change of behavior to improve the energy metrics in the world. So the consumption of voltaic panels has increased. So first, physical separation to concentrate the fraction with silver. So the main element, the most valuable element in the panels, in the photovoltaic panels is silver. So the physical separation is important to concentrate silver, and then leach using also sulfuric acid and hydrogen peroxide, and finally obtain silver as silver chloride. Looking to the future, we have to think about to recycle different types of batteries because the market is different. There are a lot of types of batteries, so we have to think to design a process to supply all those batteries in only one process. Also recovery of critical matter from secondary sources. The evolution of electronic devices, because those our equipments are changing every single day, every year. There are smartphones being launched, different types, different technologies, and also design an eco-friendly process. Since we have to think about urban mining, that's the main topic of this conversation. That urban mining is a set of processes and activities related to the production of secondary raw materials from urban solid waste. In this case, we're talking about e-waste. Think about circular economy and also the 17 Sustainable Development Goals. I'd like to thank you for everyone to be here for watching this presentation. That's my contact. Please send me a mail and whatever.